Welcome to Lesson 7, Data Types. MATLAB provides many ways of storing numbers and variables, operating on them, and printing them. We've seen lots of examples of numbers being stored, operated on, and printed. And these examples suggest that these numbers are equivalent to the real numbers of mathematics. But that's not the case. In mathematics, real numbers can be infinitely large, and they have infinitely fine resolution, meaning that the difference between two different numbers can be infinitely small. On the other hand, computers have a finite amount of memory, so there must be a limit on how large a number represented in the memory can be, and there is. Also, there's a limit on how small the absolute value of a non-zero number can be. And if you think about it, the finiteness of the memory means that a MATLAB variable can't store an irrational number. So for example, the function pi returns not pi, but only an approximation of pi. And the square root function can return only an approximation of the square root of 2. The most important thing to learn here is that the number of values that can be represented by a variable in MATLAB is finite. And by the way, that's true for any computer language. This may seem like a pretty significant limitation, but for the vast majority of problems that we want to solve on the computer, the set of numbers that can be represented by a variable is more than adequate, by far. The subject of this lesson is data types, and data types can help handle this limitation. MATLAB supports many different data types, and they provide great flexibility in dealing with numerical and non-numerical data. A data type is sometimes called simply a type, and it's defined by a set of values and a set of operations that can be performed on those values. As we've seen, MATLAB allows a given function to be called with different data types. But there's a strict rule. All elements of a given array must be of the same type. It's the array's elementary data type. In fact, the type of a MATLAB array is given by its number of dimensions, its size in each dimension, and its elementary data type. Well, let's play with data types in MATLAB. Let's start by clearing the workspace. And let's create a new variable. Of course, you do that by assigning a value to it. So we got this variable x. Let's find out what its data type is. We do that with a function called class. And it tells us that x is of type double. That's the default data type for all numerical data in MATLAB. And that's not just for variables. It's for values too. For example, if we just give it a value without assigning it to a variable, MATLAB will still treat it as a double. By the way, why is the function called class instead of type, since we're checking the types? Well, MATLAB reserves the name type for a command that prints out the contents of a file, as in type the file. Let's get a little tricky here. Of course, you know that the square root of -1 is an imaginary number, so you might expect the class to say something about that, but no, it just calls it a double. MATLAB supports complex numbers, but it doesn't distinguish among real, imaginary, and complex numbers when it's classifying them into types. Let's make some more variables. Now let's look at a new function that gives us even more information about them. It's called whos. First of all, whos prints out a list of the existing variables in the current workspace. Simple. As you can see, x, y, and z all have double over here in the class column, as you'd expect. Over here, the size column shows the array dimensions. X is a 1 by 1, since all scalars are treated as 1 by 1 arrays in MATLAB. Y is 1 by 8, as any well-behaved 8-element row vector should be. And Z is a 3 by 4 matrix. You may find the data type for AND surprising here, char. Well, how did that happen? What's the value of ands anyway? Let's see. Double. Well, is ands a double? No. Remember, this is the value of ands we're seeing here. And that value is a string whose characters are double. And how did the value of ands get to be a string? Well, it happened back here at this command class square root of -1. That was the last command we issued in which we didn't assign the output to a variable. The class command returned the data type of the output of the square root, and that happened to be a double, and returned that information as a string. Since we didn't assign the string produced by the command class to a variable, MATLAB assigned it to ands. Of course, when we enter a string, as for example when we type the format string of an fprintf statement, we have to put it in quotes to let MATLAB know that it's not the name of a variable. But when MATLAB prints a string, it doesn't put it in quotes. As we'll see in a minute, a string is just a row vector of values whose type is char. By the way, I pronounce char, char. But char is also an equally acceptable pronunciation since it's short for character. And speaking of putting strings in quotes, let's look at the type of a string that we enter. There you go, a char again as expected. So how many types have we seen so far? We got the double and the char here, but we talked at great length about one other type. That's right, the logicals. You know, the kind of value that can only be true or false. So we've seen the doubles, the chars, and logicals. Now let's learn more about these types and introduce some new data types too. As we've seen, the default data type in MATLAB is the double. That type uses floating point representation. And what's that? Well, you can think of floating point representation as being like the scientific notation that we talked about before. For example, to represent the number 12.34, we can use the fact that 12.34 is equal to 1,234 times 10 raised to the -2 power. So we can store two integers, 1,234 and -2, to represent the non-integer 12.34. In floating point representation, the 1,234 part is called the mantissa, and the -2 part is called the exponent. MATLAB uses this floating point representation for all doubles, and it uses 8 bytes of memory for each one of them. Since there are 8 bits in each byte, we say that the double is a 64-bit number. The single is the only other floating point type supported by MATLAB. The difference between a single and a double is the length. A single has only 32 bits. By the way, that's where the name double comes from. It occupies double the space of the single. That extra space allows for more digits, and so you'll sometimes hear it called double precision. But what if we know that we need only integers? For example, sensor values that are read into computers are typically integers. And in image processing, the color values of pixels are always integers. Well, MATLAB supports a number of different integer data types. In fact, there are 8 of them. There are 4 signed and 4 unsigned types. What does that mean, you ask? Well, if you don't need negative numbers, you should use unsigned data types because they represent only non-negative integers, 0 and higher. But if you do need negative numbers, or both negative and non-negative numbers, then you need one of the signed types. The other important attribute of integer data types is length. There are 8, 16, 32, and 64-bit variants of integer types, both signed and unsigned. And they differ in the range of numbers they can represent, with more bits giving a wider range. This table shows all of MATLAB's numerical types and the ranges that they span. For example, int 8, which is an 8-bit integer, can cover the range between -128 and +127. Well, why not +128, you ask? Well, the number of different values that 8 bits can form is 2 to the 8th power, which equals 256. So it can only hold 256 values, and we need to account for 0 too. The unsigned version, on the other hand, spans the integers from 0 all the way to 255. The table also shows the ranges of the other integer data types. As you can see, a 64-bit integer can store truly astronomical numbers, so it's very rare that any programmer needs integers that are larger than int64 provides. At the bottom of the table, you can see the range for the floating point data types too, and the double range is unimaginably large. But the singles and doubles can each hold values outside their ranges too. There are 2 of these out-of-range values. The first is INF, or inf, for infinity. Inf most commonly comes up when we accidentally divide a non-zero number by 0. But it signifies the result of any expression that gives a number greater than the largest value that can fit in a double. And you can guess what minus inf means. The second out-of-range value that a single and a double can have is NaN, or nan, for not a number. Nan signifies the result of an expression that gives an invalid value. For example, 0 divided by 0. So that's a look at the ranges for these types. Now let's look at some functions that deal with them. Here are a couple of useful built-in functions for checking data types. We've seen the class function before. It returns the name of its argument type. The is a function is new. It returns true or false, depending on whether the first argument has the data type whose name is given in the second argument. The int max and int min functions give the maximums and the minimums of the integer types. And real max and real min do the same thing for the floating point types. We'll try them out in a minute. In addition to the functions for checking types, there's a set of functions that do conversions among them. The need to convert a value from one data type to another comes up from time to time, and there are built-in functions whose names are the same as the desired types to be produced by the conversion. We'll see these functions in action in just a bit. Of course, what we do most often with values in MATLAB is arithmetic, and there are rules for arithmetic that depend on types. First, all arithmetic operations have no problem accepting 2 operands of the same type, and the result is always a value of that type. But MATLAB also allows some mixing of data types in arithmetic expressions. It's called mixed mode arithmetic, and there are many rules and restrictions on what's allowed and on the type of the result. These rules can be a bit complicated and somewhat cumbersome, so we'll skip them here, but if you need to work with mixed mode arithmetic in your programs, the textbook explains the rules in detail. And finally, some good news. Relational operators work with any mixture of numerical data types just fine, and not surprisingly, the result always has the same type, logical. Now let's play with numerical types in MATLAB some more. First, let's just create a few numerical variables with types other than doubles. The way to do that is to use the built-in functions with the name of the given data types that we need. For example, we just converted the double 98.76 into a single and put it in X. And we just converted the double minus 16 into an int 8 and put that in N. And we put a uint 16 into M. Let's see what we've got here. There's our 3 variables. There's their 3 types. Their sizes are all 1 by 1 because they're all scalars. That works smoothly. Well, what if we try to assign a number that doesn't fit in the given type? Let's look at some examples of that. What's happening here, as you can probably see, is that the conversion function is producing the number that's closest to the input value that can be represented in the given data type. Here we're dealing with the uint8 data type, and it can hold the integers from 0 to 255. So 500 doesn't fit. It's bigger than 255, but 255 is the biggest number, so it's as close to 500 as you can get. 256 is just a hair too big, so we get 255 again. Here's minus 1. Well, an unsigned int can't hold a negative number, so we get 0. So what's happening here exactly is we start with this minus 1, which is a double. Since any number you just type into MATLAB is a double by default, it's passed as input to uint8. Uint8 then converts that minus 1 to the nearest 8-bit integer possible, which happens to be 0. The function then returned that value as a uint8 type. So we've got a uint8 0 coming out of uint8. Then MATLAB assigned that value to k. So k now has the uint8 data type, and its value is 0. So let's look at k. It's 0. Let's look at its type. uint8. This changing of an out-of-range value to the value at the closest end of the range is sometimes called clipping, because the operation clips off the excess of the value so it'll just fit into that range. Here 500 was clipped to 255 and minus 1 was clipped to 0. MATLAB's assumption here is that you know what you're doing. You explicitly asked it to convert a big number to a type that it can't hold, or a negative number to a type that can only hold positive numbers. So rather than throwing an ugly red error message at you and stopping your program in its tracks, it silently clips the big number down to size or the negative number up to 0. So in this case, now k is equal to 0, and its type is uint8. But you have to be careful here. Look what happens if we decide to increase k to some other value that fits inside the range of its type, uint8, say 2. Okay, it's now 2, and let's just check its type. Well, its type is now double. The moment we assigned 2 to k, its data type changed. The number 2 is a double by default. So when we assigned it to k, k ceased to exist as a uint8 and became a double. It's really quite logical. If we now assigned it a string, say, you wouldn't expect k to remain a double, would you? And you'd be right. K didn't remain a double, it became a char. This illustrates a rule in MATLAB. When a variable is assigned a value of a new type, the variable takes on the new type. Many other languages work differently. A variable is declared to be of a given type, and it keeps that type. And if you were to assign a value of type char to k after it's been declared to be a double, then either an error would occur or an invisible conversion would take place right there on the spot during the assignment statement from double to char, with the same sort of clipping happening. One approach is different from the other. Not better, just different. They each have their pros and cons, but once you know what the rules are, it's all quite logical. Boring, but logical. And to keep with this theme, the boring theme, I'll show you how you can check the ranges of the types you want to use so you'll know when clipping is going to happen. There are 4 built-in functions that we can use to do that, and here's some examples of them in action. Let me clear the screen first. Bet you wish you could type that fast. We saw these same values in that table a little earlier, of course. It's pretty straightforward stuff, but it can be important when you're working with very large arrays of numbers whose range is small because of the application, such as image processing, for example, and you don't have room to store 64-bit doubles, so maybe you want to use 8-bit or 16-bit or 32-bit integers. Then this stuff won't be boring anymore. Wait, who am I kidding? This stuff will always be boring, but at least it'll be useful.